Hi, and welcome back to another video on weather radar. In this video we're going to talk about all the basic components of a radar. So we're going to start out with the master clock, and we're going to look at a block diagram and go through and follow the path of energy through the modulator, transmitter, waveguide, duplexer, antenna, receiver, and then finally the display. So we'll start out with the master clock, which is in the signal processor kind of computer area of the radar. And what the master clock does basically, it keeps all the timing for the radar, meaning that it does a lot of things, like it tells the radar when to transmit power. Also, it tells when to start to display information on the scope, how to trace the information on the scope. Also, it can figure out how sensitive the receiver should be based on the distance the electromagnetic radiation travels back from the target to the radar. And it does a lot of things. So the master clock basically is the timer. The modulator is another piece of the radar that is used basically to control the duration, the shape, the frequency of the transmitter. So in other words, it sends information to the transmitter. Also, it basically stores energy that can be sent to the transmitter at the correct time. The transmitter is where electromagnetic radiation is generated and produces a microwave signal. So it sends out a So the transmitter has a magnetron. What the magnetron does, it has a cathode which is heated. So when the cathode is heated, it repels electrons. In other words, electrons are generated by the cathode. There's a magnetic field that is generated to kind of guide the electrons into kind of a pulse. So basically what the magnetron does is it generates the electromagnetic radiation that will be transmitted by the radar itself. So some characteristics of magnetrons: they have a high peak power, very small size, very efficient operation, and a low operating voltage. So the electrons that are emitted by the cathode, they interact with an electric field, and kind of the magnetic field will kind of focus the energy, and that's what generates your microwave signal. And magnetrons are pretty cheap. You've got magnetrons in most microwave ovens, and microwave ovens are not very expensive. The National Weather Service weather radars, the WSR-88Ds, don't use magnetrons. Instead, they use klystrons, which are very good magnetrons from the point of view that they provide a very stable frequency. In other words, your wavelength doesn't really wander too much, and that's important when you're trying to measure wavelengths with Doppler radars. Other characteristics of the transmitter: the pulse duration or width, and they use the Greek letter tau to represent pulse duration. And what the pulse duration is, it's basically the time that the transmitter is turned on, typically about 0.25 microseconds to 10 microseconds. And this determines, of course, how much power is transmitted by the radar. So you can think of it as kind of like your switch on a light in a room. If you had a very, very fast hand, that could turn the switch on 10 microseconds, only 10 microseconds, where the light's on and off, and then do that many times. That would be basically the transmitter. Turning on light is, of course, electromagnetic radiation is being generated in the visible spectra. So pulse width or pulse duration was time. If you take the speed of light and multiply it by that time, that gives you a length. So the pulse length is the actual length of that transmitted pulse in terms of meters. And typically most pulse lengths are anywhere from 75 meters to 3,000 meters. Of course, shorter pulse lengths give you better resolution. Longer pulse lengths give you less resolution. But of course, longer pulses have more power and shorter pulses have less power. And then the pulse repetition frequency, or abbreviated PRF. PRF is how many times per second the radio or the transmitter is turned on. So again, going back to our analogy with a light in a room and a light switch, how many times you can turn on that light, turn it on and off, on and off, on and off, that would be your pulse repetition frequency if you measure the number of times that you turn it on and off during 1 second. Typical PRFs are 200 times per second, or 200 hertzes, anywhere up to 3,000 times per second, or 3 kilohertz. The idea behind PRFs is you can send out more pulses and get more information from the atmosphere. So the National Weather Service radars, the WSR-88Ds, have various different pulse repetition frequencies, or PRFs, to probe the atmosphere to get more information from the atmosphere. So this is how a radar works. It transmits and a pulse. After the pulse leaves the radar, the receiver is turned on and you're listening for the signal to come back. But count the number of times that the pulse goes per second, and that's your PRF. The waveguide is the conduit that takes electromagnetic radiation at a particular wavelength and guides it to the antenna. And basically it's a hollow tube, not necessarily a tube, but kind of rectangular, a conductor. And it allows the radiation to travel through that inside that conductor. The waveguides are tuned to specific frequencies. Instead of using a wire or coaxial cable to transmit the energy to an antenna, they use waveguides because of the frequencies and also the power that is involved. So it says, as it says here, of course, higher frequency signals are very lossy. Coaxial works good at high frequencies, better than wires, but not as good with radar frequencies and radar powers. So radar waveguides are the conduit, or the conductor, that takes transmitted energy and takes it up to the antenna. The duplexer is what turns on and off the antenna transmitter, or the transmitter, and sends power to the antenna, basically. So it switches the radar from transmit mode to receiver mode, and you don't want any of that transmitted power to go straight to the receiver, so it acts as kind of a check against the receiver. So you can see that based on PRFs, the duplexer has to work very quickly so that it can listen for returning signals from targets in the atmosphere. So those are some basic radar components. That's the first half. In the next video, we'll cover more radar components.